Hello again. Welcome back to EEforEveryone and part 6 of the Plant Life project. Today we're going to talk about the piece of the project that keeps everything in sync, and that's the control board, namely the processor, real-time clock, and display. Since we have completed designing the power board and understand what is required to control it, we can begin to choose a microcontroller that has the correct hardware to drive it. To serve as the UI for this project, I want to use one of the 1-inch OLED single-color displays. This will leave a lot of real estate to display metrics, expected performance, and settings menus. These displays will require either I2C or SPI control. Since there are displays that support either protocol, we can be a little flexible here. We also know the interface that the power board requires, and that's 5 PWM inputs, one for each constant current driver, one digital input to turn on the 12-volt regulator that drives the fan, and that's all. So in my search for a real-time clock, I took to the parametric search options in DigiKey, as we've done before, in part 3 of this series. Upon sorting the options, I found a real-time clock controller that supports a battery backup and was pretty cheap. It also has some SRAM on board that's battery-backed, so program variables can be stored in a quasi-non-volatile memory and then pushed to flash memory once a day or however often we can to meet our expected life requirements for the lamp. 100 years should be sufficient. The part that I chose to serve this function was the MCP7940N. It's a real-time clock controller with battery backup. Since this part uses I2C, we'll elect to use the SPI variant of the OLED display. With this determined, we need to decide on the rest of the UI. The way that I have this board visualized is that the control board will be oriented at a right angle to the power board, and then the buttons and screen would poke out through the side of the enclosure directly mounted to the control board. Therefore, I'll plan on using some tactile switches that'll poke through that front panel to use as a keypad. I want to use some resistors to create a resistive touchpad that can be fed into an analog input of the microcontroller. That will provide up, down, left, and right control on a single pin, as opposed to one pin per button. It will also provide some decoupling, since it'll take some time to charge the capacitor I'll use as a filter. For the enter key, I'll give that its own dedicated button. That'll give the option to have a shortcut with an arrow and the enter key at the same time. I'll use a photocell as a basic light intensity sensor and feed that into an analog input as well. That'll bring our total set of pin and interface requirements to the following: 5 PWM outputs, one for each constant current driver, one digital output to turn on the 12-volt regulator, that'll drive the fan, one I2C interface for the real-time clock, and one SPI interface for the display. We need 2 analog inputs, one for the photocell and one for the keypad, and one digital input to serve as the enter key of the keypad. We'll use this list of required features to select a microcontroller. However, that's not the only factor. When looking to select our microcontroller, there are a few general things to keep in mind. First and foremost, having the physical interfaces we require. This is easy enough to figure out by reading the datasheet of the component and looking at the pins and interfaces we require. Beyond this, there's personal experience, and using a development environment that you like is important. I've had good luck with the TI Tiva-C series of processors programmed with a JTAG interface. I've also had good luck with the MSP430 series from TI. The Cypress PSOC microcontrollers seem interesting. I have a few dev kits, but I haven't had much experience with them yet, and I don't want to spend a lot of time learning their new development environment. Then, of course, there's all of the Arduino compatible Atmel processors. Those are programmed through SPI with extensive libraries written. Since this is meant to be a quick part of the project and more about the analog circuits we're controlling than the control board itself, this is really more of a means to an end, and not meant to be a separate project. Therefore, if I can find an Arduino library for all of my peripherals, I won't reinvent the wheel here. If I can't find an Arduino library for the part I need, and we need to rewrite a library, we'll create that library and move forward. In this case, I was lucky and there was an existing library for every component we require. But if you'd like to see how to do that, we can go through the process of creating a library in a future video by pulling the requirements out of a datasheet and directly driving the interface required. Let me know down below if that sounds interesting. In this case, the Atmega 328P, or the standard chip used for the Arduino Uno and Nano, contains all of the hardware features we'll require. I've built a lot of boards using this chip, and it doesn't require an expensive programmer, so I think it'll work out well. I'll use the SPI programming interface to flash the bootloader with an Arduino as ISP, being a little clever and using software SPI for some of the display pins. That'll prevent the display from interfering with this bootloader flashing process. An FTDI header will allow for serial communication and programming once the bootloader is flashed. That said, the Atmega 328P does not have enough memory to use the more advanced graphics library from Adafruit. We'll be limited to a text-only display, but I think that'll be okay. This is a plant light after all. Let's pop over to the computer for a moment to look at the schematic and layout made to achieve this function. The schematic you see is very minimalistic. It contains the oscillators required for the processor and real-time clock. The other key features are the various headers that connect programming and control interfaces to the required circuits. The biggest trick here is the addition of the Schottky diode connected from the FTDI breakout's 5-volt rail to the control board 5-volt rail. This will prevent backfeeding power to the programming computer if the plant light is powered from the wall. This diode will also allow for programming and software development using power only from the PC's USB port. The resistive keypad is created with a sequence of 5K resistors, which are connected to the ADC pin through 4 switches. In this way, one button can be pushed at a time to select up, down, right, or left. Pushing 2 keys at the same time may or may not result in a normal voltage level on the output, depending on which 2 switches are pressed. Pressing all of the switches will not damage anything due to the fact that one 5K resistor will always be connected in series and cannot be shorted out, limiting the maximum current to 1 milliamp. The 0.1 microfarad capacitor connected to this pin is a simple method of debouncing the keypad signal, requiring time to charge to a valid button voltage. That's all I have to say about the schematic, so let's take a look at the PCB. When laying out this board, it was important to start with the layout critical components, namely this connector here for slotting into the power board, as well as the keypad and display module. Once those components were placed, the rest of the components were placed such that the crossing traces were reduced as much as possible, allowing for nice clean runs of traces. This also reduces the risk that we'll need to solder in jumpers to complete the layout, and reduces the amount of breaks we'll require in the power and ground planes. Optimizing the placement of parts is especially important on a 2-layer board, because there are no internal signal layers to route your signals on. A local decoupling capacitance was added throughout the board to ensure consistent performance of the digital electronics, if it's on a part of the power plane that isn't as electrically close to the power supply as I would have liked. We'll talk more about decoupling and local bulk capacitance and how that stabilizes the voltage local to a component in the next part of this series. Overall, the PCB for the control board was quite easy to route. There are no high-speed signals and no nets that require more than a few tens of milliamps. This means that the layout can get by with some imperfections and still function as expected. Once a custom footprint was made for the display module and the placement was complete, I took care to ensure that the traces connected to the oscillators on the board were length matched, stitching together places where the power and ground planes needed to split in order to accommodate the many traces traveling to and from the microcontroller. I had fun sharing my control board design with you. It's not terribly sophisticated, but it works well and makes installing the user interface into the enclosure a simple process. In the coming videos, we will begin to measure the performance of the design and turn the designs that we've been discussing into a physical lamp, meant to be hung from the ceiling with string. If you're interested in looking into my KiCad project for the control board in closer detail, the link is in the description. Most of all, I hope that you learned something great today, and I hope to see you again soon.